Hey there everybody, probably looking at this thing wondering what is this contraption and can we make one too? Yes you can, and that's going to be our project this week. Please make sure that you have a copy of the assignment Measuring Energy Conversion Efficiency. This is a project that we'll work on throughout this week. Now what you're looking at here is a gas-powered, steam-driven electric generator. And what we're interested in is how efficient is the conversion of energy starting from the gas and ending with electricity. The meter over there is measuring half a volt of electricity at the moment. I'm wondering if there are ways that I could get more electricity out of this generator. On the back of the first page, there's a diagram that you can use to look at how the energy flows through this project. And there are some questions on the next page to get you thinking about how to determine the amount of energy that's going through the project. So let's look at the components. First we have the gas coming in from the gas jet. That's methane gas, and one of the things that we'd want to know about that methane gas is how much energy is there in each amount of gas that's burned. The gas is a source of potential energy stored in the chemical bonds of the methane gas is released when it's converted into heat in the combustion reaction. Now that energy then, that heat energy is going into the can, and as the can, which is made of steel, gets heated up, inside the can there's some water. And then the water particles, since they're being heated up and energy is being added, they start to move faster and faster, and they become steam, and the steam is pushing through a little hole up here, and then that steam is pushing a turbine made of some metal that was bent, and then as it spins, this part right here is an electric motor. When you put electricity into a motor, it makes the motor spin, but when you spin the motor, electricity comes out. You run the motor in reverse, it's an electric generator. And that electricity is going down here to this meter so that I can find out how much energy is being produced. I want to compare how much energy is going in to how much energy is coming out to find out how efficient it is. Now there are a number of things that can be adjusted in this project. You can think of some things that you might try to make this thing go faster. One thing is the design of the turbine part, this rotor that's spinning. In the past, students have tried many different designs, and some of the things that they've done have been to change the size of the rotor. Sometimes they could be big, sometimes they could be small. Which one do you think would get more energy from the steam and spin faster? One thing that these two have in common is that the turbine blades are bent as though to catch the steam better. Some students in the past have made them flat, not bent. This one has a whole lot of little vanes to catch the steam, more than this one does. You can make the blades short or you can make them long. Here's one that was made, someone made a really small one with lots of little tiny blades and bent them to catch the steam. These are some examples of ways that you can change the design of the project to test which would be the most efficient, which one would get the most energy out of that steam. So what we'll work on this week is building this generator, and we're going to compare the efficiency of the energy conversion in this process to the energy conversion in other processes, such as turning sources of food from one into another. Let's take a look at this part right here, how much energy is in that fuel source. One thing that we need to know is how much energy there is going into the generator. So we have to know what volume of gas comes through the gas jet in each amount of time. And we need to know what is the fuel value of each volume of gas. How many joules of energy are released when each volume of gas is burned. So what I'm going to do is I'm going to measure the amount of gas that comes out of the gas jet, and using this bucket of water in which I have a 1 liter graduated cylinder turned upside down. It's filled with water, and there's a Bunsen burner down there, and when I turn it on, it'll fill up the graduated cylinder and push out the water. And I'll use the timer to figure out how long it takes to fill that up with 1 liter of gas. So, turn on the gas, start the timer, and I'll turn it off when it gets to 1 liter. Each 1 liter of methane gas has a fuel value of 38,000 joules. So that's a lot of energy. If I were to take this 1 liter of gas and light it on fire all at once, it would release all of those 38,000 joules of energy at one time. I wonder what that would look like. Alright, so we're almost down to 1 liter, and I'll stop the timer as soon as we get to the 1 liter mark. Almost there. Almost there. Almost there. Looks like I'm going to hit 1 minute at the 1 liter mark. Exactly. Okay, so I hit the 1 liter mark in exactly 1 minute. That's very convenient for math. Every 1 minute that we burn the fuel, we generate 38,000 joules of heat energy. That's what goes into the can and into the water, and ultimately into the spinning of the turbine. What we want to find out then is how much energy comes out on the other end in the generator. Now I wonder, what would this gas look like if I were to burn it? Let me fill this the rest of the way, and I conveniently have something to light it with here. And I know that you like to see things blow up, so let's try to blow this one up and see what happens. All right. What does 38,000 joules of energy look like? Let's take a look. Okay, put that up, light it on fire. Not very spectacular. Okay, now we've looked at how much gas is coming out of that jet in every minute. And if you know how much energy there is in each amount of gas, then you can figure out how much energy is coming through that flame every minute that it's burned. Now, in order to get this thing going, there's a bit of a startup cost. That means that energy has to be put in before you can get energy back out. So for example, when I started this out, the water that was in the can wasn't boiling. It had to get up to the boiling temperature before it could make steam and make this thing spin. If you were trying to figure out the startup cost of getting this going, you'd want to know something about making that steam and how much energy it takes to do that. So you can think about that when you're working on answering the pre-lab questions on the design of the generator.